Hello friends, and today we'll be discussing about data exploration and data analysis of breast cancer Wisconsin. It is the diagnostic data set of breast cancer where this is the classification problem. We have to predict whether the cancer is benign or malignant, that is it can cause cancer or it will not cause cancer. So malignant is causing cancer and benign is that it is not dangerous. So how do you get the data is that you go to this Kaggle. So I'll show you. What you do is you go on Google, write breast cancer Wisconsin, and hit on this Kaggle link. You'll be directed to this page, and what you do is you hit this download. Okay, and when you will hit this download, it will be downloaded as a zip file. You go show in folder, and what you do is you extract this file. And when you extract this file, it will ask you certain things, the path, destination path, hit OK, and this is your downloaded file, okay, data. Now what you do is you just see that this is breast cancer Wisconsin data, okay. So now we go to home, and this is the Jupyter notebook which I have launched. And how do I launch it? That I just hit Jupyter notebook from the Anaconda command prompt. So you get this Jupyter notebook, and now we have created a folder before. We have done iris analysis tips data set. So data analysis folder is created. What I have done is I have already downloaded the file. So you go to upload and you upload this file. I think downloads breast cancer and this data. So data.csv, since I already have this file, I will not upload it, but this is how you upload the file. Okay, so now I have created a Python notebook for here. So, and how will you create it? You go to new and Python 3. So a new notebook will be created. Therein you can write your breast cancer data or breast cancer prediction. So you can create a new notebook, but since I already have it, I will not use this. So let's start with this notebook. What I have done is I have imported a few libraries. Okay, so what you do is you import libraries, pandas and numpy. This for linear algebra, and this is for your data frame and pandas for better representation of data. Matplotlib and Cbon library are used for plotting, right? What I do is I import warnings, filter warnings, ignore so that warnings do not come. So that is the code for this. Now I have to load this data. So I just load the data. So I load the data. I hit 2 here and shift enter. So this is the heading, second heading. So now when I load the data, what happens is the data is being loaded as pd.read csv data csv, which has been in my working directory. And then what happens is this is still going on. See, this is, as you can see, the asterisk sign here and waiting sign. So we'll just wait till it's loaded. Okay, it's been loaded. So now df.head, we see the first 5 entries of this, and we see that there are 5 rows here by default and there are 33 columns. Okay, so you can see ID, diagnosis, radius mean, texture mean, perimeter mean, area mean, and so on. So we can see the worst also, and we have this last column of unnamed 32, and we see all these entries, right? Okay, what next? We go and hit the df.tail and we get the last 5 columns. Okay, so you can see this diagnosis has only M and B. Now let's see whether is there anything else in diagnosis. And first check the shape of the data. My shape of the data is 569 rows and 33 columns. Okay, so now let's see this describe some statistical information, and T is for transpose. That means suppose this count mean will come here. I have created this in the heading. So I get all these 33 this thing here, and this is the value. So we count all our 569 rows, and this mean is, as you can see, that we are getting this mean, which is that means we will be requiring some kind of standardization to get suitable data. Okay, and we can see the standard deviation also is something like this, and then is minimum maximum value 25%, 50%, and 75%. This is what this describe tells us. Okay, let's explore further. So now I want to see how many unique values are there. So df.diagnosis.unique, that is the code we write, and we find that there are only 2 values in diagnosis, that is M and B, malignant and benign. Now DF diagnosis, I want the value count of it, how many are there. So benign are 357 and malignant are 212. Let's have a plot for this. So if I want to show you how does it look like, it looks like this, and this is an object. Okay, this is not numeric, this is M and this thing, but this is giving me a count. So benign, malignant, you can see this is 212 and benign is 357. Okay, let's hit further. Now what we do is we clean and prepare the data for further training of the algorithm, so that this can be fitted in algorithm. Now my algorithm will let's see which I have dropped this ID because ID is not needed in my data. Okay, so if I just show you df.head, okay, that is already yes. So this ID is not needed because I don't have to do anything for that. And also this unnamed 32 which we have seen here, this is also not needed. Okay, so what I do is I will drop these 2 columns. Okay, so I just drop these 2 columns. This is what I write, and then I check the head. Okay, so I check the head as, and I see that there's 31 columns, that means these 2 are dropped. Now what else? Let's see what else we can do with this data. Now I since I have to train an algorithm and an algorithm will not understand this M and B, so now I have to change this into numeric. Either I can perform label encoding, or I can map it, or I can also use an if or else loop. Okay, so I use this diagnosis and I use this dot map malignant as 1 and benign as 0, and then I tell it to show me this that has been converted. So see, you can see this, that this has been converted, malignant as 1 and benign as 0. So if you have got a dangerous tumor, it will be treated as 1, and if it is non-dangerous, it is 0. Now what if I want to see how many null values are there? So this is how I see it. df dot is null dot sum, and this will give me that, see, all are 0, that means there is no null value here, so we don't have to replace the values. Okay, easy task. This is a code for if you want to apply if and else. Okay, now we see the correlation. This is important because we have to determine whether is there any relation between the 2 variables or not. So we see this df.corr, since this um, correlation, if you want to see and examine here, you can just see that radius and diagnosis have high mean, have high correlation. Similarly, perimeter and this has relation 74.74, and area mean is 0.70. Similarly, you can see this concave point mean is also highly correlated. Okay, and you also see that radius mean with perimeter mean has high correlation, 0.99. Also see that the texture mean, okay, perimeter and radius again, see, the same 0.99. Area mean and radius mean 98. Area mean, perimeter mean 98. So we can just see that the area, radius and perimeter, they have high correlation. Okay. Similarly, we can observe it here also, that compactness, concavity, have they got any high relation? So this 83 compactness mean, if we map it here, concave point mean, so they are also highly correlated. Okay, now let's plot it and see how does it show. So I have also plotted this thing, that plt.hist, that is histogram, and I want to see this mn0. This is also after converting it to 1 and 0 also you can plot it. So plot title is this, diagnosis. M is 1, B is 0, and this is what it shows again, the number of tumors of cancerous and non-cancerous cells. So now we go to, okay, this is the correlation diagram for which we have plotted earlier, of which we have seen earlier. So I set the figure size as 2020, and then Heatmap provides this, SNS provides this resource, this facility. So I do the correlation mapping here, and NO true means it will write these numbers inside. Okay, so again we can see here, let's see that the diagonal radius mean and the diagnosis are positively related. Radius mean and perimeter mean again are 9999 highly related. So we can see here the relation, correlation, high correlation. Now what I do is, since I want to first see the mean columns, and as you have seen that there are mean 1 2 3 4 5 6 7 8 9 10. Okay, mean, and this is standard error. So we've got certain standard errors like 10 or so, worst also. So we are plotting it for scatter plot for mean columns. What we do is, I assign a column in that an array. I will assign all these: diagnosis, radius mean, texture mean, perimeter mean, area mean, smoothness, compactness, concavity, concave points, symmetry, and fractal dimension mean. Okay, and what I do is, I plot an pair plot for this to see the correlation among these three, among these all. Okay, and what I do is, data is df, and you go to these columns. Hue is diagnosis, that means 0 and 1 it will be plotted, and palette I have taken as rocket. Okay, you can take any. So now you see this has been plotted, and so let's just see this. Now you see, focus on this figure. This is highly linear. These all. Now what does this show? This is perimeter mean, okay. And what is this area mean, okay? This is radius mean. This is area mean, perimeter mean, radius mean. What can we derive from here? That these are highly correlated. Radius mean, and when you go up and you see that this is radius mean and perimeter mean, okay. So that means there is a problem of multicollinearity here, and there's perfect linear relation between radius, parameter, and area attributes. This means that there's a presence of multicollinearity. Now what does this multicollinearity mean? That these features are very highly correlated and they're dependent on each other, and this will affect the performance of the model if we will include these in our data set, okay, in our further data. So what we have to do is, we have to take only one among these three. So we will select one. Next we see multicollinearity, and another thing, that is, see the concaveness, the concavity, concave points, and the compactness means they also show some kind of multilinearity, collinearity. Okay, so I am making this hypothesis. Now I have to check whether it is true or not. Let's see. And if you want to see the label, check the label. So here's the diagnosis. This purple color is 0, that is benign, and 1 is malignant. Okay, this pink one is malignant. So let's see now. Now multicollinearity, I have described that this is means that they are highly linearly related, and this also undermines the significance of independent variables. The other variables would be undermined, and the model will not give them preference. So what I use it, how do I remove this? I remove it by using the partial least square regression, or I can use the principal component analysis, which reduces the number of parameters. And regression methods, they will cut down these numbers of parameters or predictors. Okay. Now what I do is I have to visualize the correlation matrix to understand this thing. So what I do is, this is the code which has been given in the SNS Seaborn documentation also. So this is from where I have taken it. So correlation is df.corr, and this is how we write it. Mask for the upper triangle, since I want this upper triangle, and for lower, if I want a lower, I'll just write L here. Okay. So mask is equals to np.0. I'm using numpy here, and I'm using triangle upper indices from mask is true. So what I'm doing is I am creating this triangle, this kind of a matrix by this code. Then what I do is I set the figure size as 2020, and the cluster color map I give it as CMap. This is what the map, that's how it looks like. And then I draw the CMap and giving parameters, passing the parameters inside. Okay. And the layout is tight layout. Okay. So this is what it will generate. And as you can see that here also I am getting the same thing. I am getting perimeter mean, area mean, and see, area mean related to radius mean 0.99, again related to, now you see here 0.82 concave points, and for the highly correlated. So this is what it looks like. Okay, so we can verify here the presence of multicollinearity. And now this is the description that radius mean has a correlation of 1 and 0.99, and perimeter mean and area mean columns. Okay, now this shows that there's high multicollinearity, and we have to pick just one. So we can pick radius. Okay, because it is a cell, so it will have radius, and so linking it that yes, radius is something important, so we can pick radius from this. Now another place is that where's mean and worst column. Now you see one point that radius mean has high correlation with radius worst column. So let's just find out this thing. It is 0.97. Radius mean has high correlation with radius worst column. So just track it. Radius worst 0.97. See, radius mean and radius worst. So that means that the worst radius has got high mean. So we can see that these means are related to the worst column, right? So what I can do is I can drop this worst column, because they all are just redundant of the mean values. So, and we also find multicollinearity between compactness, concavity, and concave points. So we can just take one, and I will take compactness here. Now what you do is you drop all the worst columns, so that we are left with only few parameters for algorithm, and we can predict the data accurately. So we take only mean here. So what I do is I drop this worst column, all the worst parts here. So what I do is I drop it, x is equals to 1 again. Then what I do is I then drop all the columns related to perimeter and area also, to remove multicollinearity. I will remove them: perimeter mean, perimeter SE, area mean, and area standard error. Okay. Next I will drop it. This is how I drop it. Then lastly we will drop all the columns related to concavity and concave points attributes also. So this is how I will remove it. And then what I do is I verify what is my DF column look like, and this looks like this. So we've got these one: diagnosis, radius mean, texture mean, all mean, and smoothness, compactness, symmetry, SE. This is what we are left with. Okay. So now what I do is now I draw a heat map again to see whether is there any high correlation. So again I use the same code here. I just copy pasted it. and what we see here is that now there is no high correlation. You can just see that's only 0.73, and see, there is no high correlation. So we have removed the multicollinearity. Okay, right? Okay. Now what you do is, now the next point is building the model, which we shall see in the next video because it is quite long. So that's all for this, and stay tuned for the second part. Thank you.